Good morning, everybody, and thank you for attending today's webinar. My name is Matthew Byer, and I am the Inside Sales Representative here at ThermTest. Today's webinar is on phase change materials for energy storage, presented by Dr. Sophia Malona, our Principal Research Scientist. I would like to just mention the upcoming webinar on steady-state thermal reflectance using the SSTRF method on electrical components will be presented by Patrick Hopkins on May the 4th, so be sure to sign up for that webinar. And without further ado, I'll hand it off to my colleague, Sophia.
Hello, and thank you very much for attending today's webinar. Today's agenda, we will talk about the phase change materials, what is a battery thermal management system, and the categories of the phase change materials used for them, their advantages and disadvantages, and finally, what are the criteria for the selection of the suitable phase change material. Then I will present you the transient hot wire technique with which we measure our phase change materials. I will present the advantages of the technique, and then I will present our THW L1 device and the software coming with the device. And I will finish my presentation with some measurements taken with the THW L1 of PCMs and the THW accessories used. At the end of the webinar, you can write down, or while the webinar, you can write down your questions and I will be glad to reply them. So, what are the phase change materials? They are substances that they are able to absorb or release latent heat in order to keep their temperature stable. And they are widely used in the thermal management applications because of these special characteristics. The applications of the phase change materials are in solar energy, in heat pumps, in spacecrafts for the thermal control, in the electronic industry, in the waste heat recovery systems, in pharmaceutical products, and in electrical vehicles and hybrid electrical vehicles. So, what we need in order to have a good battery thermal management system? It needs to have an optimum operating temperature operation range, where for each cell and each module of the battery, the heat will be rejected to in the environment when the environment is hot, and some energy will be coming to the system in cold climates. Additionally, we need to have small temperature variations within the cells and the module, but also among the different modules of the battery system. It needs to have low weight and be easy to be packed, to be reliable and low cost, and of course to be easy to get serviced. And of course, and this is very important, um, uh, it needs to have a good ventilation system in case there are any hazardous gases produced during its generation. There are three different methods of the battery thermal management systems. These are the active, that can be air or liquid components. It's the passive, that can be liquid or phase change materials, or a combination of between active and passive methods. There are different categories of phase change materials, as you can see in this graph. In our case, we will talk about the systems that there is a thermal energy storage and a latent heat is coming or leaving the system. And especially we will talk for solid liquid systems that they are separated, which are the PCMs, which are separated also in three categories, and these in subcategories. But all these phase change materials, depending on the category they belong, they have some advantages and disadvantages. The organic ones, they have the advantage that they have a very large temperature range, they have low vapor pressure, they are chemically stable and recyclable, but in the most of the cases they are flammable. They have low thermoconductivity, that it's not good, and they have low volumetric latent heat storage capacity. On the other hand, the inorganic PCMs have the advantage that they have higher thermoconductivity than the organics. They have low cost and they are not flammable, but they are corrosive to metals, and they have high volume change during the whole temperature range. The last category, the eutectic ones, they have very sharp melting point, which is very positive, but they have very high cost that make them not ideal for the use in battery thermal management. So, what are the criteria in order to select the right PCM for the thermal management storage? They need to have one of these criteria mentioned here, like high latent heat of fusion, to be easy available and low cost. Um, no corrosion is ideal. They need to have high density, high thermoconductivity, to be non-toxic, to be chemically stable, and more other. The PCMs that they will be selected will depend of the use and the melting point that it should be in the application range, and should have the most of these criteria mentioned here. So, as I mentioned at the beginning of my presentation, we measure our PCMs with the transient hot wire technique. As the most of you already know from previous webinars, the transient hot wire technique is the primary technique for the measurement of thermoconductivity of liquids, because of the full theory behind it, in order to measure the thermoconductivity. So in order to calculate the thermoconductivity of the fluid, we record the temperature rise of a thin wire when this is immersed inside the fluid after a step voltage is applied to the wire. And because of that, the wire is acting as a heating source that transfers heat from the wire to the fluid, and in the same time as a resistance thermometer from which we can record the temperature rise of the fluid. Because a temperature field is applied around the wire, this can be described from the equation of conduction, which can be solved as the temperature rise of the fluid as a function of the logarithm of time. From this straight line, and the slope of this straight line, we can calculate the thermoconductivity of the fluid. The advantages of the transient hot wire technique is that it's accurate, it's convenient, it's an absolute technique, which means that in the case of the double wire, there is no need for calibration, but in the case of the single wire sensor, as our sensor, there is a need of only 1 point calibration with one fluid, and then it's ready to use. It's very convenient. There is no convection present during the measurement, but if there is any convection present, even natural convection, it's easy to be detected from the results. The measurements are really fast, only 1 second, and the wire is heated using constant current, and from the temperature rise of the wire we can calculate the change of the electrical resistance of the wire and calculate the thermoconductivity. Which means, because we calculate the thermoconductivity from the slope of the straight line, the highest the thermoconductivity, the lowest the slope, the highest the slope, the lowest the thermoconductivity of the fluid, and of course it's following the ASTM standard D7896. This is the transient hot wire, the THW L1. It's suitable for measurements of fluids, of liquids and pastes. The thermoconductivity range is from 0.01 to 2 watts per meter Kelvin. Additionally to the thermoconductivity, it measures the thermal diffusivity of the fluids and calculates the volumetric specific heat. It's suitable for a very wide viscosity range, up to 10 million centipoise, and the the preferred measuring time is 1 second. The repeatability of the measurements is 1%, and the accuracy 5% for very high temperatures and pressures. There are 3 different models. The THW L1 that has a temperature range from 10 to 200 degrees, and pressures up to 20 bar. The THW L1S from -50 to 200 degrees, again for pressures up to 20 bar. And the last model with a wider temperature range from the THW L1E for temperatures from -150 to 300 degrees. These low temperatures below 100 degrees can be reached with a liquid nitrogen system. The volume of the sample is 20 ml, and as I mentioned earlier, it follows an ASTM standard. It's very easy to take measurements. It's very simple. The fluid is poured inside the sample cell, and because the time, the volume, and the measuring time are very short, allows accurate measurements without any convection, and the cell can be pressurized up to 20 bar or 30 bar in case of the THWL1E model. Then the measuring cell with the sensor can be placed inside the integrated temperature platform that allows the temperature control without the need of any external heating or cooling system. In the later, when we take the measurement, the THWL1 software allows automatically control of the isothermal steps of the temperature from 10 to 200 degrees for the basic model, or up to -50 or -150 for the other models. And the Smart THWL1 software verifies the quality of the results at each temperature step, and also recommend changes if it's needed, and all at the end of the test gives a results report either in a printed report or in an Excel file where the data can be further analyzed, or additionally the user can receive the results in their email. This is the first page of the THW software. In that page, you can see that there is this unique detect power option where when the sensor is inserted inside the fluid, when the user press the button, it takes a thermal conductivity measurement using a standard power. It calculates the thermal conductivity of the fluid, and according to this first thermal conductivity measurement, it recalculates back the suggested power for that should be applied to the fluid for accurate thermal conductivity measurements that would be allow measurements with a temperature rise from 2 to 4 degrees. Then the user has the option to start, if it saves the results, or start a new sample, open another previous file, save any measurements. As you can see here in the right side, there are different settings that the user can follow. Then the user can select to make his own manual schedule or make an automated schedule with the temperature step that they will select. You can see here that it's suggested that at each temperature step, when the temperature is stabilized, the power can be detected before the starting of the measurements for more accurate thermal conductivity results. And additionally, the user can modify the number of the tests or the delay time for each measuring step as according to the wishes or the needs of him. These are some results of ethylene glycol. Here you can notice that there are the measurements. You can see the temperature of the fluid and the name of the sample. The measuring time is 1 second. The power applied, the temperature rise of the fluid, and then the thermal conductivity, thermal diffusivity, and volumetric specific heat. The quality of the measurement shows if the user is good to move on with the measurements, and this is directly dependent from this residual graph on the bottom that you can see here. When it's between plus minus 0.05% according to the theory, then the measurement is very good and the results accepted. There are three in the THW software. There are three quality messages. The first one, as we mentioned, is the good one, that the measurement is good. All the conditions are satisfied. There is no external noise or electronic noise for the measurements. There is no vibration. There is no convection, so the user can move on. The next one is the okay, that the measurement can be good, but probably the user needs to slightly increase the power during the measurement. And the last one is the poor, that means that maybe the user needs to increase or decrease the applied power in order to be between the 2 to 4 degrees temperature rise, or there is any external noise during the measurement. But there is one exception. In the case of conductive fluids like nanofluids, if the temperature rise is between 2 to 4 degrees, then and the results are repeatable and follow the same trend as the previous results, then the results are accepted and is a false reading of the software. I will continue here with some measurements of the PCMs we measure here in the lab. The first one is the N-hexadecane. From the right photo, you can see that the room temperature it's a bit flaky, which means, and it's from the results we saw that when it's melting gets different shapes. So in order to pour this sample inside our cell, we need, as we did with the most of the PCMs, that they were uh, solids at room temperature, we heat up both the sample and the measuring cell up to one temperature. Here we heat it up until 80 degrees, and then while it was warm, from the bottom of the cell we pour the fluid inside the cell, and we close the bottom of the cell, and we set the cell and the sensor inside the device. And then we ran measurements. First one run was cooling of the fluid, and then heating, and then cooling and heating again of the measurement. You can see that there is a melting range that is about 10 to 15 degrees, and is not the same for the cooling and the heating of the fluid, which is something that we were expected. And also there is an anomalous thermal conductivity reading at this region because of the endothermic and the exothermic procedures of the fluid. Additionally, you can see, and this is what I mentioned earlier, that there are differences in the results during the cooling and the heating procedures of the sample in the area where it's solid. And this is because while the fluid was solidifying, it was solidifying in the different shapes and not in the same position every time around the wire and between the sample. So it caused different uh, uh, some different shapes appears inside the sample. The next one is the N-hexadecane. This was liquid at room temperature, but we decided to heat it up a bit. So we heat up until 35 degrees, and we ran measurements again from cooling, heating, cooling, and then heating again. Also in that case, you can see that there is, as it was expected in the melting cooling region, there is an anomalous thermal conductivity reading, but in that case there is a different, more sharp melting point during the cooling and the heating of the fluid. But again, you can notice that during the cooling and the heating, probably there are different shapes of the fluid while it's solidifying. That's why there is a difference in the thermal conductivity. The next PCM is the N-hexadecane. It was solid at room temperature, flaky but semi-solid. In this case, again, the PCM was melted up to 50 degrees, and then the measurements were taken from high to low temperature, and then to high again, and low again, and then high again. In that case, the melting or cooling range is smaller than before and more sharp as before, but still there is this latent heat range that is very obvious, and you can understand where it's the melting and cooling of the sample. And if you also notice from the photo, there are different shapes and different levels of the sample in the solid condition. And this can be seen also in the thermoconductivity results in the solid region, but the results in the liquid region are very repeatable, extremely repeatable in all the cases. The next sample is the paraffin wax. That is the sample that is very much used from many authors in the literature. It's cheap and very easy to find them, and has a very well defined and sharp and repeatable melting point that is almost the same for both the melting and cooling of the sample. You can see also that the results during the heating and cooling excuse me, are are very repeatable for both the liquid and solid phase, and this is because the solid phase is very homogeneous and there are not different surfaces um, appear during the solidification of the paraffin wax. The last sample is the polyethylene glycol 6000, is one more sample that is used in the literature, and it's not impressive if we see the results, because it has a very sharp melting point, and that it's very obvious. It's very easy for the user to see, and very important, the thermoconductivity results are very repeatable, not only in the liquid phase but also in the solid phase of the PCM sample. That's why it's one more reason that we were not. It's something that in the beginning we were not expecting it, because of this shape when we receive the sample, but it means that when it's heating up and then melting in the same bucket, everything is well organized and homogeneous around the wire and in the cell. Oh, sorry, I had one more fluid. This is the 1-tetradecanol. This one, I can say I was expecting to have better results because of the shape, but judging from the different uh, shapes that even the sample in the room temperature had, we noticed that during the same procedure, the cooling procedure of the liquid PCM, there were different results during the different runs. The melting region is sharp, it's very small, but now there is a reverse. In the previous fluid, the thermoconductivity of the solid phase was higher than the liquid, but in that case it's reversed. It's going to lower thermoconductivity values, and I can understand why it has many uses in the literature. Some accessories that they can be used during the measurements of the PCMs is the PCM cell that it was used during this measurement for that this cell allows the pouring of the fluid from the bottom of the cell, and the spring-loaded lid allows the expansion and the contraction of the fluid with the volume change with the temperature, and as a result the fluid of the sample is always in contact with the wire for accurate thermoconductivity measurements. And another cell can be used is the observation cell, that the user can see the changes of the sample while it's changing the temperature or over time. So if the user wants to see how the sample is solidified at lower temperature, it's easy to see, to observe it. And also, if there are any particles inside that can sit on the bottom of the cell, it's also very easy to notice it. That was the end of my presentation. Thank you very much, and I'm ready to answer your questions. We will take a couple of minutes in case you have any questions. Otherwise, anytime you can send us an email and we can reply back to any of your questions anytime on this subject or in the THW related. There is one question saying, can thermoconductivity be measured continuously through a range of temperature? With the THW software, the user can make a schedule with all the temperature range that wants. For example, in the measurements you saw, the schedule was to go from 80 degrees every 10 degrees down to 10 degrees, for example, and then go up. So at the end, I had nothing to do. I just to from time to time to observe the thermoconductivity results, and then at the end to receive the analysis of my file. So all these 3-4 runs, all the measurements were taken automatically through the THW software, and the only work I had to do is to prepare the schedule before I start my measurement. So yes, I haven't done anything else. So yes, I can measure the thermoconductivity continuously for all the temperature range. If you're saying the instead of point to point, I'm not. I think I reply to you because there is in the THW L1, there is the built-in temperature platform that allows the cooling and the heating of the sample over the whole temperature range. So yes, you can take all the measurements as you wish, and you can take as many measurements you want at each temperature. I cannot see any more questions. As I mentioned earlier, feel free to send us your questions, even even if it has to do something with a webinar. You will receive the webinar recording in the next 2 days. But also, if you want to ask, if you have any questions about the THW device and the different models we have, please feel free to send us an email. Thank you very much, and don't forget to register to the upcoming webinars. Thank you.